Good morning, everyone. Welcome to my presentation. I'm Zhiyu from Automatic Control Laboratory of ETH Zurich. Due to visa reasons, unfortunately, I cannot join the conference in person. I'm looking forward to meeting you sometime in future. Today, I would like to share our work on model-free nonlinear feedback optimization. First, I want to acknowledge the help from my advisors, Lauren and Severio at ETH, and my former advisors, Professor Jianping He and Professor Xinping Guan at Shanghai Jiao Tong University. Let me introduce the problem that we consider. This work is motivated by this question: how to achieve efficient operation of a physical plant. Suppose that we have an objective function phi that depends on the input u and the steady-state output y of this physical plant, and the steady-state map is encoded in the equality constraint here, and d is the disturbance inside the system. For example, in the optimal power flow problem, the input u would be the active and reactive powers, and the output y would be the voltage measurements. In the numerical optimization paradigm, we need to explicitly formulate this problem. In other words, we need to know the exact expression of the steady-state map H and the value of the disturbance D. These two requirements can be restrictive in applications. In contrast, we consider such an emergent paradigm of feedback optimization. The central idea is to interconnect an optimization-based controller with a physical plant. We will always utilize the real-time measurement of the output y, and then we iteratively generate the new input u that we feed into the plant. In this way, we can drive the plant to an efficient steady-state operating point. Such a closed-loop architecture is robust against model mismatch, and it is also computationally efficient. Existing feedback optimization algorithms are first-order methods that rely on gradients. When we calculate the gradient due to the chain rule, we need a central model information called the input-output sensitivity, H. We have several strategies of estimating this sensitivity. However, they are accompanied by additional efforts. And also we need to achieve sufficiently accurate and fast learning. Otherwise, the iterations would suffer from suboptimality. So a natural question is, can we remove the requirements of estimating the sensitivity and make the whole procedure to be model-free? Well, it turns out that a classical paradigm called extremum seeking can address this issue. The central idea is to add perturbations, usually sinusoidal signals, to the inputs, and then learn gradients via averaging or integration. This type of method is mainly suitable for low-dimensional systems and unconstrained problems. The main reason is that we do not want the sinusoidal signals that correspond to different elements of the input to interfere with each other. So we need to restrict our attention to low-dimensional systems. Extremum seeking provides one way of estimating the gradients. There are also other works that are inspired by zeros-order optimization to achieve closed-loop optimization. These works mainly consider static maps and use multi-point estimates. In this setup, when we inject the input, the output would immediately be the steady-state output, and we need to actuate the system multiple times at one iteration. In contrast, in this work, we consider system dynamics, and we only require one actuation step per iteration. Another popular paradigm is reinforcement learning. In comparison, we consider dynamical systems represented by state space equations instead of Markov decision processes, and we focus on steady-state performance instead of cumulative reward. To summarize, our central motivation is to fulfill model-free feedback optimization. Compared to existing works on feedback optimization, we want to remove the requirements of estimating the sensitivity. Compared to extremum seeking, we want to handle constrained problems and high-dimensional systems. Compared to reinforcement learning, we focus on steady-state performance. Let me introduce the details of the considered problem. We want to select an input u to drive a physical plant to an efficient steady-state operating point as determined by this problem. We consider system dynamics represented by this nonlinear state space equations. We make several assumptions on the system dynamics. We assume that the plant is globally exponentially stable and it has a unique steady-state map. In other words, we consider a plant that is pre-stabilized, and then we further investigate how to drive it to an efficient operating point. We can define a rate of change of the plant, and we assume that this rate of change mu is less than 1. This assumption can be satisfied. For example, if we have a continuous time plant, then we choose a large enough sampling period above a certain lower bound, so that the obtained discrete time plants after sampling satisfy this property. We also assume that the overall objective function is Lipschitz continuous and non-convex of the decision variable, the input u. Recall that our central motivation is to achieve model-free feedback optimization. Existing feedback optimization algorithms require the knowledge of the sensitivity because they use the gradient-based update rule, and gradients encode this model information. To fulfill model-free control, we need to consider optimization without gradient evaluations. It turns out that a useful technique called gradient estimates in the zeroth order optimization literature can well serve this purpose. The central idea is to use function values and then scale it by the random vector to construct a stochastic gradient estimate. For example, in the left figure, we want to estimate the gradient at the circle point. What we do is to evaluate the objective values at the neighboring points of this circle point. And then we select random directional vectors to construct a stochastic gradient estimate. This estimate is useful in the sense of expectation. When we take expected value of this estimate, it will give us a very good estimate of the direction of the true gradient. We have several types of gradient estimates depending on how many function evaluations they require. The first one is the 2p point estimate. What we do is to select p basis vectors and then scale it by the finite difference. We also have 2-point estimates, where we select a random directional vector and then scale it by the finite difference. We also have 1-point estimates. We scale the random vector by only one evaluation of the objective value. Now I would like to invite you to think about this question. For our setup of closed loop optimization, we inject inputs, obtain output evaluations of outputs. Which type of estimate would be suitable for our purpose? I guess you already have your answer in mind. The answer is actually the 1-point estimate. The main reason is that at 1 point W, we want to select the construct gradient estimates and obtain new inputs. We only have one chance of injecting input and obtaining the evaluation of outputs. We don't have the freedom to inject both W and W plus delta V as required by the 2-point estimate. So in this case, the 1-point estimate would be mostly suitable. You can see that when we calculate the second moment or the variance of the 1-point estimate, it is kind of large because they are dependent on the square of the objective value. Such a high variance will influence the solution accuracy. Later, we will present a design to further improve the solution accuracy by reducing the second moment of this type of estimate. Now let me elaborate on the design and analysis of the proposed model-free feedback optimization controller. We focus on unconstrained problems. The design of the controller and the closed-loop interconnection is shown in this figure. We will utilize the real-time measurements of the output y, and then we evaluate the objective value. We further subtract it by the historical value, and then scale it by a random vector to construct a gradient estimate. In this case, when we calculate the second moment of this type of estimate, it is significantly smaller than the previous standard 1-point estimate, as we shown in the previous slide. Once we construct such a stochastic gradient estimate, we do great gradient descent-based update to calculate a new candidate solution. We then perturbed it by exploration noises, delta Vk, where that delta is the smoothing radius, and we obtain a new input and feed it into the plant. Such a closed loop will be run for several times to drive the physical plant to an efficient operating point. You can see that the design of the gradient estimate plays a central role. Such a design is actually inspired from the recent breakthrough in zeroth-order optimization, or more specifically, the one-point estimate based on residual feedback. The difference is that since we utilize the real-time measurement, the objective value we obtain is approximate instead of exact. Such a difference will pose additional challenges in terms of analysis, and is one of the contributions of our work. Let me present the theoretical guarantees of such a closed-loop interconnection. The main takeaway is that given the size of input P and the number of iterations set beforehand T, we can suitably select the smoothing radius, delta, and the step size eta to ensure that the convergence measure would be of such an order given in the theorem. Since originally we consider Lipschitz continuous objective function, it is not necessarily differentiable. To analyze the convergence, we focus on first-order stationary condition with respect to the smooth approximation of the original function. Such a smooth approximation can be made extremely close to the original function, and we can use this accuracy requirement eta as one of the requirements to further design the smoothing radius delta and the step size eta. The result is a bit complicated. Let me provide more interpretations. So the convergence measure, the first order stationary condition, would be given by the right-hand side. We have two parts. The first part, purple part, corresponds to the descent-based update of the controller, and the second, blue part, corresponds to the dynamic response of the plant. In the second part, we contain the rate of change mu as we see before. The interpretation is that for a rapidly decaying plant, or let's say for a continuous time plant, we choose a very large sampling period. In this case, the rate of change mu would be very close to zero. The convergence measure would only contain the first part, the purple part. If we set a large enough number of iterations beforehand, then the convergence measure would be very close to zero. In this theorem, we characterize the stability of the interconnection. The main takeaway is that we need to suitably select the smoothing radius delta and the step size eta, as we see in the previous theorem. Then the interconnection of a stable plant and the optimization-based controller will remain stable. In this case, we analyze the difference between the state after we inject the input and the corresponding steady state. On the right-hand side, both terms contain the rate of change mu as we see before. The interpretation is that if the plant is rapidly decaying, then the right-hand side would be very close to zero. Consequently, the difference between the state after we inject the input and the corresponding steady state would be very close to zero. Currently, we present the design and analysis for unconstrained problems. Similar extensions for input constraints are available in our paper. What we do is to use Frank-Wolf type updates or projected gradient descent. We can further analyze the optimality and stability of the closed-loop interconnection. Let me present more details on the numerical results. We consider a nonlinear system where the nonlinearity comes from the quadratic residual term in the state space equation. And we consider a non-convex objective function that is the sum of a concave function and two convex functions. We compare the proposed algorithm with several competing methods. One is the stochastic extremum seeking. The other is first-order feedback optimization. We consider three cases. When we have the exact sensitivity, it is the baseline. The second case is the sensitivity matrix is corrupted by noise. The third case is we use online sensitivity learning that starts from the approximate sensitivity. As we can see in the right figure, the stochastic extremum seeking converges relatively slow. When we know the exact sensitivity information, the first-order feedback optimization gives a relatively good solution accuracy in a relatively small number of iterations. However, when the sensitivity information is inexact, as we can see in the red line, the solution accuracy is influenced. Sensitivity learning helps to address this issue. For the proposed method, we can achieve a comparable accuracy guarantee as the sensitivity learning approach. But more importantly, we can further handle non-differentiable steady-state map. However, you can see that in the initial phase, the proposed model-free controller, the purple line, converges relatively slow. So a natural question is, can we exploit approximate model information to further improve the sample efficiency of the model-free methods? It is a very interesting question, and we have provided an answer by designing a hybrid approach. We will show our paper in the recent period, so please stay tuned. To summarize, we consider a feedback optimization problem. The contributions are threefold. We consider a general setup with non-convex objective and nonlinear discrete time dynamics. We propose a fully model-free design where we utilize the real-time measurements to construct gradient estimates. We also provide a finite time non-asymptotic characterization of optimality and stability of the closed loop interconnection. If you are interested, you are welcome to visit our paper on arXiv. I would like to thank you for your attention, and I'm happy to answer any questions.